Hey everybody, welcome back. We are live again and going on strong to our next talk. Before we do, I just want to remind you once again that if you have any questions, the Q&A section, that's where you should ask them. I think everyone has been following that, and hopefully you've been having fun in this conference as much as we can, and going to the sessions to just go to the breakout rooms and meet some people. Hopefully you've met someone new in this community. And now, without any further ado, I'm gonna let Mrinal come in and talk us about securing our applications. It should be fun. See you in a bit.
Hi, everyone. My name is Mrinal Wadhwa. I work for Ockam, which is an open source project and an open source company. And my talk for today is focused on secure and dependable systems. But before we get into that, the actor model, which is sort of the basis of Erlang processes in Beam in Erlang and Elixir, is really well suited for systems that model the physical world. So, you can imagine things like connected machines, robots, machines in factories, devices in our house, etc. Whenever you have like lots of concurrent entities communicating with each other, Elixir is a really nice tool to build systems like that that have these concurrent entities. The reason that's the case is, this is at a very high level, pretty much all connected machines. They have, there's some kind of sensor that senses some information in the physical world. It turns that into a message, sends it to a state machine of sorts that is modeling the state of the device. This state machine makes some inferences, and based on those inferences, out comes some kind of action that is then communicated back to an actuator that acts on that action in the physical world. So at a very high level, all such sort of connected physical world systems look like this. But there's also a lot of like state machine replication going on, right? So there's, you might imagine that inside the device, there is a tiny state machine that only knows about the information that is available to a particular device. And then in a cloud service, there's a bigger state machine that knows about the state and context of lots of devices and can make more informed inferences. So, maybe run like a machine learning model. If you're familiar with the Nest thermostat, they popularized the whole idea of learning-based tuning of connected devices. And this is not just like replicating the state machine twice or like just edge devices and cloud services. Oftentimes, this will be like several hops of replication. There may be some decision making that's happening inside the device, some other decision making that's happening in some kind of edge computer that is closer to the device. You could imagine a machine in a factory that is dedicated to making decisions about several machines in that factory. And then obviously cloud service. A real world example I can think of is this. I was involved in a project a few years ago where we had sensors that were sensing traffic on a street, and they were able to make better decisions because a nearby computer could have combined information from several sensors, like detect a tram passing on the street, etc. So the topic of my talk today is how do you secure messages between all of these sort of actors in your system that may be distributed across several environments. So how do you secure these messages? And And securing these messages is how we can make these systems dependable. So an interesting nuance here is that while we like to draw simple, client talks to server over TCP, messages within modern applications rarely flow over a single direct point-to-point transport layer connection. This is never the case, or rarely the case. Even in simple web applications, if you think about a web app, you probably have some kind of load balancer if your app is in production, and then several servers in the backend. So in this, these two arrows that I have are two transport layer connections. So even in simple web applications, it's rarely the case that you have a single transport connection. If you have a more complex system, maybe based on several microservices, you may have a API gateway and then several microservices talking to each other. So in the path of a single request and a response, there may be several transport layer connections. If you have, I don't know, Kubernetes-like environment, there will be several more transport layer connections because there are things going through load balancers, ingress gateways, and proxies of different kinds. If you have a message broker-based architecture, maybe using Kafka or RabbitMQ, then all your microservices are talking to that broker over some kind of TCP or transport layer connection, and your clients are also talking to the microservice, to the message broker with a transport connection. So there are many transport layer connections going on in these systems. And oftentimes these transport connections aren't within the same trust boundary. You may have, your message broker may be an external service. So it's not even within your private network, if you will. Your microservices may be talking to external services. In the physical world, you may have a low power wireless protocol gateway where there's radio protocol involved. So this is interesting because in this scenario, you can imagine that it's not only isn't there a single point-to-point transport connection, there are multiple transport layer protocols involved in the flow of messages from the client to the microservice. There may be LoRaWAN in the first hop and then TCP in the second hop and so forth. If you have a edge environment like a smart factory or something like that, then this whole data center environment or cloud environment may get replicated in a tiny microservices setting inside the factory. So you can imagine this number of transport layer connections in the path of a single message continues to grow. So my point is we want to secure these messages in transit, because if we can secure them, we can make our systems dependable. But these messages, as I said, rarely travel over single point-to-point transport layer connections. So to think about the security of these messages, a useful model is the stride threat model. The stride threat model lists each letter in the word stride lists out a set of threats. And in my second column here, I have the corresponding desired properties. So we want protection against spoofing of identity. We want to know who's at the other end, who's the sender of a particular message. We want to make sure that the message wasn't tampered en route. We want to know that the message actually came from where we think it came from. We may want to protect the message from leaking information to make our systems private. So we may care about confidentiality. And we, of course, want to make sure that when messages are sent, they actually get delivered. And we want to make sure that the right messages come from the right source. So if a machine is saying it's on, only that machine should be able to say that it is on, because that's the only authority on that piece of information, and other machines shouldn't be able to say it. So to achieve these desired properties, protections against these threats, to achieve identification, authentication, data integrity, confidentiality, etc., we use typically two tools in current systems. The first one is this idea of trust in network boundaries. So to take a simple example, what we might do is draw a trust boundary around our load balancer and our web servers and go, okay, within this trust boundary, we can assume that data traveling over the wire is safe. So we draw a trust boundary like that using, firewalls and network boundary type of settings. If you have a message broker, we might draw a broader boundary and have all our microservices be inside this private network. And this works if the number of entities involved in your system are small. It starts to break down if your microservices are talking to some other cloud service, or maybe your message broker is an external service, and suddenly you can't put things inside a closed boundary anymore. And turns out in modern systems, we've realized that the network perimeter or boundary-based security model just doesn't scale. Here's a paper from Google which says, as companies adopt mobile and cloud technologies, the perimeter is becoming increasingly difficult to enforce. If you dig into that paper, they say, key assumptions of the model no longer hold. The perimeter is no longer just the physical location of the enterprise. Google's experience has proven that this faith in network boundaries is misplaced. Access should instead solely depend on credentials. And we need to enforce fine-grained access to different parts or different resources. This idea is not new. It has been over the last maybe 8, 9, 10 years, been getting formalized in lots of different system designs. There's a book called Zero Trust Networks, which basically says don't trust network perimeters and build security from the ground up inside your application. There's a NIST paper around it, but basically the assumption in this model is that the network, both internal and external, or even private networks, can be hostile. External and internal threats exist on the network at all times. Network locality should not be sufficient for deciding trust in a network. And every device user network should be authenticated and authorized. And this should be a dynamic, data-driven decision-making process. This idea even showed up in the cybersecurity executive order from a couple of weeks ago. Essentially the same thing. Inside and outside traditional network boundaries, there are always threats. And at the bottom of the order, they highlight least privileged access should be applied to every access decision. So this brings me to our second tool for protecting against tampering and snooping of messages, which is TLS or SSL, because the Erlang package is still called SSL, but that's an old name for TLS or transport layer security. And that's our kind of primary tool in modern systems to protect from message tampering and ensuring data integrity and confidentiality of messages. But the problem is, messages within modern applications rarely flow over a single direct point-to-point transport connection. And TLS is tightly coupled with the length and duration of the underlying TCP connection. So it's technically possible to decouple TLS, but practically speaking, it is very tightly coupled with the underlying TCP connection, which means that the data integrity and confidentiality guarantees are lost at every transport connection hop. So if you have several transport connection hops in the data flow of your message, at every network intermediary, at some edge gateway or some ingress gateway or at a proxy, your TLS guarantees are lost entirely. This violates that basic idea of security that we need to embrace in computer systems sort of security design, which is this idea of principle of least privilege. These network intermediaries end up having way more authority than they need. And think about it, right? Like there's your message broker, for example, needs to route messages, but it doesn't need to see the contents of the messages, but it does. A gateway, a LoRaWAN gateway hanging on a pole on a street doesn't need to see the messages. It just needs to route them. But in a lot of system designs, it does. And this situation's pretty bad. Like there are devices you can buy for your house where they don't even try to protect network transport at all, right? So my primary point is trust is an application layer concern. It is not a network layer concern. We can't build applications any longer by just assuming, some network proxy or load balancer or TLS terminator will handle network security, and we can just build our applications. We learned this lesson pretty well in web applications for a long time. Like we've added authorization frameworks and all sorts of different things in web apps, but in more sort of real-time systems, we kind of still rely on networks as our protection, and that falls apart pretty quickly. So trust is an application layer concern. How do we enable applications to build trust in a message? How do we ensure that an application can reason about the trustworthiness of every message? A distributed application with lots of actors, with lots of state machine replication and real-time data flows. So the basic building block we need for that is secure channels. Secure channels is the general idea. TLS is a secure channel protocol, but essentially a secure channel kind of looks like this. There is an initiator of the channel, there is a responder to the channel, and the initiator sends out a message, the responder responds. There's public key cryptography involved in this phase. It's called the authenticated key exchange typically, and using public key cryptography primitives like Diffie-Hellman key exchange, you essentially end up with a shared secret that is computed and never actually transferred over the wire. So both parties end up with a shared secret. Once they have the shared secret, they can then use symmetric key cryptography and more specifically authenticated encryption to encrypt the data that is being sent between this initiator and responder. But the problem we have is in protocols like TLS, this secure channel is tightly coupled with the underlying TCP connection. So inside Ockam, the open source project, we've decoupled it. So you can create a secure channel with these two lines of code. And remember, our goal was to make it easy for applications to reason about trustworthiness of messages. So we wanted to make it simple to create secure communication. This is the first building block towards that goal. So if you're a responder, Bob in this example in line number 3 creates a secure channel listener with the identity key Bob, and Alice then creates a secure channel with Bob using the identity Alice or the identity key pair Alice over the routes to Bob. And I'll talk about routes in more detail in a second. But with these two lines, equipped with these two lines of code, your application can create any number of secure channels with any number of entities. So it's not a single TLS connection between two machines in your data center. You can create any number of these ad hoc secure channels. They're very lightweight. What this does is takes the ability to create secure channels away from hard-coded network config files that require all sorts of complex config that are very easy to make mistakes with, especially if you're using something traditional like OpenSSL. Instead of doing any of that, you can just make two function calls in Elixir and you get a secure channel. Okay, but why is this different? The reason this is different is that traditionally, your sort of network stack kind of looks like this. You've got the IP protocol, you've got TCP on top, You've got TLS on top, which provides the network security, and then your application is communicating over those TLS channels. But in the Ockam protocol design, over TCP sits a tiny binary protocol called Ockam routing. And Ockam secure channels then sit on top of Ockam routing. The benefit of this is that this Ockam routing protocol can describe multi-transport protocol routes. So we can have secure channels that can span multiple transport layer protocols. So you could have any IP-based protocol sitting underneath and have a secure channel where the first hop is HTTP, the second hop is TCP, or the first hop is UDP, the second hop is TCP, but the secure channel is still end-to-end. So when the underlying transport layer connection terminates, the secure channel does not terminate. The secure channel guarantees are end-to-end. And you can, of course, do this over low-power protocols. So you can do this over Bluetooth, you can do this over LPWAN. And the trick, of course, is to keep the messages small and compact and provide a mechanism to plug in these transport implementations for the Ockam routing protocol. So let's look at some code to understand what this really means. So an Ockam worker is really just a easy way to create these actor state machines. So it's kind of like a gen server behind this use Ockam worker macro. But here I'm creating a simple Ockam worker called printer, which whenever it receives a message, just prints that message. And I start that worker by saying printer.create at address printer. These addresses are important because we want machines to remotely route messages to workers on other machines. This printer has an address called printer, and I can craft a message which the Ockam routing protocol will understand. This message would look like this. The payload of the message is hello, and the onward route of the message is printer. And note that this route is a list, and currently we have only one address in this list called printer. So then we call this function Ockam router.route message, and it sends it to the printer, and a printer prints it. Cool, right? But this is not very useful if you're just within one machine. It starts to get really interesting if you're sending messages across many machines. So to do that, you have to create a transport layer connection. So on the machine that is running our printer, we create a TCP listener by running this command. And then on a different machine, we create a TCP client which says, okay, connect to that same port 3000 on the other node. And once we have this transport connection, we can write a new kind of message that is routable with Ockam. And this new message says, my onward route has 2 hops in it. The first hop is a TCP hop. The second hop is the name of the worker I want to send this message to. And the message, of course, is still hello. And we then again call the same Ockam router route message function, and it delivers the message to the machine over TCP, and then from there, locally routes it to the printer worker on that second machine. So interesting, but we don't have to stop here. We can have many transport layer hops. So you can have a route that describes 3 transport connections. And this can be useful in scenarios where you don't have a direct TCP route to the machine that has the printer worker. Maybe you're going through some kind of intermediary service, or you're behind a NAT and you need to exit the local network. So in all sorts of scenarios, you can then start to leverage this multi-hop routing capability. And like I said before, notice here that I can have hops in other protocols, right? So I can describe the onward route in this case as the first hop is Bluetooth, the second hop is TCP, the third hop is TCP, and then there's a printer worker on that third hop node. And this message would just get routed just the same. All right, so now that we understand that there's this ability to route messages over multiple transport layer protocols, and when this message is actually sent over the wire, it's turned into a tiny binary format. So over the wire, this particular message here probably looks like about 20 bytes. So these messages can be pretty small. All right, now let's create a secure channel over this multi-hop route thing. So remember from a few slides ago, we were able to create secure channels as Alice. So in line number 8 here, I'm creating a secure channel as Alice, but I'm creating it with Bob, who is 2 transport layer hops away. So my route to Bob describes a TCP hop to port 3000, and then another TCP hop to port 4000, and then Bob's secure channel listener is on that second hop away. And like we saw before, this can be an arbitrarily complex route, and it would still get traversed as long as that physical transport layer connections actually exist. So on line number 10 here, we then craft a message that passes through the channel. So what we're saying is this time around, once the secure channel is established, take the message hello Ockam and run it through the channel. And the channel is a secure channel that remembers the route to Bob in its internal state. So when on line number 8, the secure channel was created, it now knows the route to Bob in its internal state. And then in line number 10, when we craft a new message through this channel, this message enters the channel, gets encrypted, gets delivered to the other end, and gets decrypted on the other side by simply calling Ockam router.route message. So if you look at the sequence diagram for this thing, it kind of looks like this, where you've got an app on one side that wants to send the message hello Ockam to some worker on the other side, but it does that through a secure channel. So the first few messages are the establishment of the channel, and there's this handshake that occurs over multiple transport layer hops. And once the channel is established, we send hello Ockam, it gets encrypted and gets delivered to the other side, gets decrypted and delivered to the worker on that other side. So this is how we're able to achieve end-to-end encryption. You may have heard this term before in human-to-human messaging apps like WhatsApp or Signal, and a lot of the cryptographic ideas that are implemented inside Ockam are actually borrowed from Signal's protocol design, especially their handshake protocol called X3DH. But what's unique about Ockam here is that while Signal was specifically designed for a 2-hop interaction between 2 parties that are sending each other messages via a server, Ockam is more general purpose protocol that can describe all sorts of complex multi-hop end-to-end encrypted connections. And an interesting thing to note here is that a secure channel provides us protection against all of these threats, not just information disclosure. So oftentimes when you say encryption, people assume the goal is confidentiality. But not only confidentiality, the goal with secure channels is to provide all of these desired properties, especially data integrity and authentication. And this often gets lost, but essentially the value of a secure channel is not just that it is hiding your information, it's that it is guaranteeing that the information you just received is the information the original sender actually sent, right? And your notion of the original sender is in fact correct, and you're not being spoofed by a spoofed identity. So guarantee of authentication and data integrity are actually more important in end-to-end encryption or encrypted secure channels in general than confidentiality, because all applications need data integrity guarantees to be a dependable application. Not all applications require the confidentiality guarantee. However, end-to-end encryption or secure channel is our only tool in computer science to actually deliver data integrity guarantees in an efficient way. So we need end-to-end encryption if we want a system where we can trust information from remote machines. So let's look at a quick practical example. Let's imagine that I was building a heart rate monitor, and I want to go out on runs, and I want this heart rate monitor to measure my heart rate when I'm running around, and maybe I don't want to carry my phone with me, so I add a mobile connection or cell modem to my heart rate monitor. It has a SIM in it, and it can deliver messages over the internet. So the typical design would look something like this. You would have some service on the internet called the heart rate service. The heart rate monitor would send the data to the service. The phone would also connect to the service over a different transport connection, and the service would then deliver the data to the heart rate application. And maybe we want the heart rate service to cache these readings if my phone is offline. So the purpose of the heart rate service here is to route information and to cache information. And if we use TLS, which is kind of the best practice, best case scenario, and isn't in fact used by a lot of real world systems still, but if we follow the best practice and we use TLS, then this is what our data flow would look like. The reading would start at 80 beats per minute on my heart rate monitor, and then it would become some encrypted value over the wire. It would reach the service, and it would become 80 beats per minute again. And then it would enter a new transport layer connection and become a different encrypted value, and then finally reach my phone. The problem with this is that the heart rate service has unnecessary authority. It can see all the data, and it can potentially manipulate all the data. It can even just generate readings when there are no readings being sent by the heart rate monitor. It's free to do whatever it wants, really, right? There is no trust relationship between the heart rate monitor and the heart rate application. The trust relationship is between the monitor and the service, and the phone application and the service. So with end-to-end encrypted secure channels, you can eliminate this. You can have a channel that is just routed by the service. So the service gets to see who is talking to whom, but doesn't get to see what data is being transferred. And turns out like lots and lots of connected devices are built like this. If you've got a connected outlet in your house, the purpose of the service is to route commands when you're away from the house. But it actually gets to send commands at will. So if the service is compromised, anyone can take over outlets in your house or a machine in a factory, because the architecture for that would also look very similar. If you've got a connected lock, very similar scenario. If you've got a doorbell, this one's really interesting because there's a popular vendor of connected camera doorbells that has built-in network that monitors a large number of connected doorbells and can create a picture of who is moving along different streets, when the actual purpose of the doorbell was to just deliver video to me, the owner of the doorbell, but somehow it delivers a mechanism to do to collect information from a large number of doorbells in one place. So it becomes a honeypot of data that can be, even if you can trust the vendor of the service, if that service is compromised, that honeypot of data can be compromised. Similarly, if you've got a smart city like flood monitoring system, this is very similar to the system I was involved in designing several years ago. And if you've got like a flood monitoring system, and your first hop is a LoRaWAN hop, and your second hop is a TCP connection, and then you've got a intermediary vendor and another TCP connection, all these points in the middle become points of vulnerability, points that have way more authority than they need to. And with end-to-end encrypted secure channels, you can have you can sort of remove these intermediaries from your trust architecture. And if you look at like real world connected systems, this problem starts to get really, really bad. This is a pretty realistic, smart building management system, and hundreds of gateways and hundreds of intermediary vendor backend systems and several system integrator systems all have unnecessary authority. And in these scenarios, the complexity in the attack surface kind of becomes unmanageable, and proprietary data is leaked. Security essentially becomes untenable. We can instead have end-to-end encrypted secure channels and remove all of these points of weaknesses in our system. So this is what we're trying to do at Ockam. We're trying to create a framework or an open source collection of tools that provides a suite of cryptographic protocols that help you tackle and build these end-to-end secure communication distributed systems. And secure channels is just one of the building blocks, but it's a foundational building block. So routing and secure channels was kind of our first two steps. And now we're focusing on several other components. So some of those components are around managing keys and identities. So to do encryption, you have to issue keys to a large number of devices. And now these keys have to be rotated, they have to be revoked. And so we needed some kind of sort of general protocol to show that a rotation of a key or a revocation of a key was in fact authorized by the owner of the key. And so we've got a protocol in there that proves change events on an identity. So if you've got an identity, let's say Alice, you can show that Alice had key number 1 at time 1, and then it rotated its key to key 2 at time 2. So there's a protocol, a cryptographic protocol in there that shows provable change events. You can use it for all sorts of different tools like key rotation, key revocation, metadata updates in an authoritative way, etc. Another interesting protocol in there is this idea of identity profiles. So let's take your car, for example, right? Your car has a manufacturer that needs to send software updates to your car. And then your car may be using a location service that needs to provide you with maps and guides, right? Today, what happens is because the car can be identified and has an identifier that is known to the manufacturer, and it's the same identifier that is known to the location service provider, the location service provider and the car manufacturer can collate their data sets and identify that this person who went to location 1 has the name X, has this age, has bought this kind of car. So privacy contexts are not separated in most connected systems these days. They're intermingled together, and vendors can correlate your data to learn even more information about you. So inside Ockam is this idea of identity profiles, where very easily you can create lots of different identities, almost ephemeral identities for different privacy contexts. So your application can choose to use a different identifier for the manufacturer context and a different identifier for the location provider context. So if someone is building a privacy preserving, privacy respecting IoT system or connected car, this is a very useful tool to build that kind of system. And then all the secure channels you create and all the credentials you collect are now isolated within these profiles. Another interesting tool available in the toolkit is selective disclosure. So traditionally, you may be familiar with this idea of signing or signatures, cryptographic signatures. The traditional algorithms that are used to do cryptographic signatures or to issue credentials like certificates, they disclose all the information that is signed in a certificate. So, if you go to a bar and let's say you have a credential that is your driver's license, if you present your driver's license to the bouncer at the bar, the bouncer can see all the information in that driver license. They can see your age, your address, etc., your blood group, your name. But actually, the bouncer only needs to know whether you're above 18 or not. And the same kind of thing happens when connected devices talk to each other and prove authorization using signed certificates or credentials. They reveal way more information than they actually need to reveal because the certificate contains all that information signed under one signature. So inside Ockam, we use a more interesting signature algorithm called BBS+, which allows for selective disclosure. So you can collect a signature on 10 attributes, but present a proof of possession of signature on one attribute. So imagine you can get a driver's license that signs 10 attributes about you, but to the bouncer at the bar, you can present a proof that you are above 18, but you don't show any other information that was signed in that credential. This is very useful in access control type connected machine scenarios, maybe accessing a machine in a factory. And the same primitive also allows you to be anonymous. So one of the attributes that is signed in a credential may be your name, right, or the identifier of a device. And because we can hide certain attributes that are signed, we can do a proof that I'm above 18, but not reveal my name. Similarly, a device can do a proof that it is authorized to start a machine, but not reveal who is starting the machine. And then finally, another interesting tool that is available inside Ockam is this idea of trust policies, where you can have granular set of rules about who gets to do what, or who has authorization for what. And all of these tools, we are then combining into creating higher level protocols. So Enrollment is a protocol that every developer of a connected system ends up inventing from scratch. So we're building a general purpose fleet enrollment protocol that takes care of how you issue unique credentials to each device, how they onboard into your system, etc. So on these basic cryptographic building blocks, we're building a collection of higher level protocols. Fleet enrollment is the first one. We expect to do things like firmware updates and credential lease management, etc. next. All right, so that concludes my talk. Ockam is an open source project. It is written in Rust and Elixir, and the Rust libraries are a little more mature than the Elixir libraries at the moment. And we are actively looking for people who want to contribute and help out. We even mentor first-time contributors. So if you're interested, please check out Ockam on GitHub. Thank you. That concludes my talk.
Thank you for the talk. And we did go a little bit over, so we'll try to answer at least 2 questions and see what we can do here. So because we have a few, so maybe afterwards, if you can answer some in the Q&A directly to the people, that would be great. But so the first one is, how can you integrate Ockam with existing applications and services? Can it be a layer below your existing services, or does it need to be integrated deeply into the communication?
It can be layered below your existing communications. We are essentially building what we call portals. And the idea is that you could, imagine a TCP connection that comes from one end. We wrap, so it looks like you're connecting to a regular TCP endpoint, but then this portal takes that TCP message, wraps it in an Ockam routable message, traverses a path, and then on the other side, decrypts the message, unwraps it, and presents it to the actual server. So you can kind of tunnel existing protocols through end-to-end encrypted secure channels in Ockam. And because Ockam secure channels can be tunneled inside other Ockam secure channels, this can create all sorts of complex secure topologies. But short answer, yes, you can describe you can kind of layer this below existing systems.
Cool. And so the other question would be, frequently distributed apps on the beam are criticized for security. The only protection is the cookie param. Do you see Ockam being used to create a secure replacement for distributed Erlang EPMD?
Yes, absolutely. I think we are thinking broadly, not just between Erlang to Erlang VMs, but you could certainly use Ockam to do secure communication between Erlang beams instances.
Cool, great. Again, thank you so much for the talk. And yeah, if you can hang out in the Q&A section, you should be able to reply to people over there, and so make sure everyone gets their question answered. Thanks.
Yeah, thank you. Thanks, everyone.